All right, today we're going to talk about waves some more, part 3. And the reading is relatively short, just pages 251 to 255. And that covers the part of what we'll be talking about today, not entirely. And that's from that same book, Thurman. Okay, so we're going to start by looking at a picture from last time. So I mentioned capillary waves and gravity waves, and this image shows an example of both in water. So here you can see these little sort of centimeter scale waves that are generated by the wind. And the point here was that the surface tension is the main controlling force is trying to flatten these waves out. And that is in contrast to let's see, yeah, so over here we have the large waves here are much bigger, and it's gravity that's trying to restore those mainly. Both forces are active, but the gravity will be the dominant one. And the other thing that you can see here is the superposition of, so the wind is blowing over here as well, and you can see capillary waves on top of these larger gravity waves. And you can also see a wave, part of it has broken here. So let's continue with water waves and talk about one of the sort of the most famous types of waves, tsunamis. And so tsunamis result from a sudden change in the topography of the seafloor. And that is due mostly, so it's mostly those tsunamis occur due to fault motion, mostly. So in other words, earthquakes, and not in a certain category of earthquakes. So faults where there's vertical motion. So some part of the seafloor is moving up or down. And not generally those with horizontal motion, or what we call strike-slip earthquakes. So not So generally, a fault like the San Andreas that is mainly moving things sort of north and south, generally wouldn't be expected to trigger a tsunami because it's not really affecting the elevation of the water. It's when the water is like suddenly lifted or brought down. The exception would be unless the earthquake triggers some other kind of activity like an underground avalanche. Okay, so the wavelength for tsunamis is generally greater than around 200 kilometers. And that's why, as I mentioned last time, they're shallow water waves. Because the seafloor is, no more generally, no more than a couple kilometers. So the wave base would be far below where the seafloor is. So the entire column of water feels the tsunami waves as they pass. The heights are generally unnoticeable, less than half a meter when in the open ocean. But they slow down and pile up at the shore. So we saw just like the wind-blown waves, wind-generated waves. As the seafloor gets less deep, they slow down, and the energy needs to go somewhere, and it goes into increasing their elevation. And finally, they're not a breaking wave. So in popular culture, sometimes you see, the tsunami looking like that. That's not what they look like. It's more sort of a wall of water. Sort of more like so not a breaking wave. It's more like a sudden, extremely high tide. Or actually, it's a high or low tide, right? High and or generally alternating. So typically, there'll be several of these. So there'll be very high, very low, very high, very low. And that's why these have been sort of misnamed tidal waves, because they're kind of like, they have an effect like a tide, but they don't have anything to do with the tides. So it's not really a great name. The tides being more controlled by the gravity of the sun and the moon. The reading has some interesting case examples of famous tsunamis that occurred in different places. So the next topic is refraction, and that's a topic that is relevant for water waves and all the other waves as well. So we'll start by kind of just describing the process, and then I'll give some examples of how it applies, what the significance of it is for water waves and seismic waves. So the basic idea here is the waves change directions when their speed changes, in general. or when they encounter a medium that has a different, that they travel at different speeds in. So this is, for example, light hitting a prism, right? The light's traveling this direction, and then it goes off in different directions. So the main relationship that you need to know about is called Snell's law, and the idea is, so we have a material that the wave travels at some velocity 1, and then there's another medium where the velocity is different. And the relationship is that if light or some other wave is coming in at some angle we'll call I, it's going to continue at some other angle. I'm just drawing this so that you can see what a right angle is. It's going to continue off at some other angle R. And the relationship is that the sine of I divided by the velocity 1 is equal to the sine of the angle R divided by the velocity in the second medium. So obviously if the velocities of the two are the same, I and R will be the same. So it just, where the velocity is not changing, the light or any old wave will just continue going in the same direction. It's the change in velocity that induces this change in direction. And so why does this happen? So if we think about like a train, so this would be like a wave crest here. So you could imagine a series of waves here, and they're going to encounter, let's say this could be water, right? And we're in the deep water here. And we're in the shallower water here. So the wave is going to get closer and closer, right? Just continuing in this direction. Those are just multiple wave crests. And then some part of the wave hits the boundary. And we can think of a wave as going kind of in all directions at once. So when this hits here, it sends off. It's like throwing a pebble into the material. So it is the effect of sending energy in all directions. And by the time this wave is moving, right? So by the time it gets here, this wave has already gone quite a distance. So this is just starting to. So at this point, in all of these waves hitting are creating these same sort of thing, each one a little bit smaller as we go this way because it's just been less time. So we can connect those, and that's the new wavefront. So that wavefront is at a different angle, right? And it will continue on So we could call this the refracted wave. And this would be for the case, for the example where velocity of the second velocity v2 is less than the velocity that the waves are traveling in the first place. So you can see that because, for some, so at the moment this wave touched, it traveled in this medium, right? It traveled this far before that length is equivalent to the length, or is equivalent to this, right? So in the same amount of time, the wave traveled this distance. We could just call it x. Once that same wave kind of started to go into this material, it only traveled this far. So we can, just looking at it graphically, you can see the velocity is slower in this material, and you could imagine how these would be bent if this was the opposite case. I'll just sketch that right here. So this would be for v2 greater than v1. When these waves come in, they end up coming off like that. So the wave bends, the wave shallows, okay? And this is, there's a video that's attached, so there's two videos to watch that are posted, and the second video goes into more detail in explaining this, and gives a nice example for seismic waves. Sort of a guest lecture. Okay, so what are the implications of this general property of refraction? So for water waves, you'd expect they're coming in from all directions. They generally approach the coast at all angles. But they bend and end up aligned nearly parallel to the shore. So if you've been to the beach, you've probably noticed that most of the waves seem to be coming pretty much so if this was land, and this is the sandy beach, the crests of the waves are usually, coming in at some pretty much parallel to the shore, and that is because, even if they're coming in at some larger angle. So Snell's law works. It doesn't need to be a sudden change. Incrementally, it's kind of like calculus, like a little bit of a change, a little bit of an angle change. Okay, so as they slow down, they tend to curve into alignment with the beach. So this one probably is connected out here to something coming in at some angle. And then, of course, they may be coming in, from this side as well, right? And the same thing tends to happen. So it's just an example. And then the other thing that happens is if you have sort of something sticking out into the some kind of rocky formation, it's sticking out. So maybe it's sandy here, and there's some rocks. We could call this a headland. The opposite things happens here. So a wave, the wave coming in will, let's make that a little bit longer. Well, it's not really the opposite, but it tends to curve as well, right, towards the headland. Right, so the wave energy is kind of directed at the headland, and that focuses erosion processes. So this refraction process kind of concentrates energy and wears away on things that are not straight about the coast. So the energy of waves is constantly straightening out the coast. So shorelines tend to straighten because waves focus their energy of erosion on headlands. And another implication of Snell's law is, so for seismic waves, you might have noticed when I drew the Earth, so there's an earthquake here, seismic waves tend to curve upward. And that has to do with the fact that as material, so if this is Earth, cross-section to the Earth, density increases, the rock density increases under the pressure of overlying rocks, and waves tend to travel faster at higher, when they're traveling through higher density material. And so that means that the velocity increases as you go down, the velocity of seismic waves. So for seismic waves, they generally curve upward. Because there's higher velocities deeper levels. And so that's this illustration here, right? You can see it kind of curving upward because, and I should have written V1, because the velocity is increasing as you go down. So another way that waves change direction is through reflection. Oops. And the general rule here is that waves reflect at an angle equal to the approaching angle. So to illustrate that, if we imagine there's some change, some surface. This could be like light in a mirror. Could be water waves coming into just like a concrete wall. So they're traveling at in some direction. Let's say that, define that direction by this angle alpha. The wave is going to bounce off in the same, at that same angle. And we could illustrate this the same way that we did with refraction. So if this was our train of waves, okay, so this sets off, this is coming in at this angle. When this hits, it sets off waves start to go off in all directions. So let's see, this one, by the time it gets to here, has gone about this distance, about 3 of those, right? And I've drawn about 3 of these. I didn't draw it perfectly, but maybe you can get the idea, right? So it's kind of like, it's like a mirror image of refraction, and the velocities are the same, right? It's all in the same. Everything here is the same velocity. So what happens is you get equal angles on both sides. So there's a video that I'd like you to watch next on reflection and refraction, and it describes this. It goes into a little bit more detail, but hopefully makes it a little bit, helps clarify some of these ideas. So go ahead and just flip over to that video on YouTube. That's going to be a separate link, and if you're watching this from Dropbox, it'll just come up automatically.